So what shall we do? We have time domain, we have
Laplace domain.
Laplace domain. Some operations we do in time domain.
Correct.
Addition, multiplication, etc., etc. What is the corresponding, operation in Laplace
In the
domain?
Laplace domain.
I think we have seen those indirectly. Maybe we can just list down.
We'll just list it down formally. Okay.
So I'll just write it as operations. In time domain, and the corresponding one in maybe basic one is addition, addition or subtraction.
Yes.
Well, let's say if I have two signals, f1 of t and f2 of t. Both of them will have integral f1 of t power minus st dt.
Correct.
Plus again integral.
Correct.
So
That's
it's
right.
just sum of
It's just sum of the two Laplace transforms, right?
Laplace transform.
So capital F1 of S and capital F2 of S.
Yes. Another one may be, let's say if I multiply a signal with a constant, scalar multiplication.
Correct.
Let's say some k times f of t. Again, when you integrate take the transform,
K is a constant, it will come
outside.
out of the integral.
So it will be k times f of s.
Yes. I think along the way we have just used this
We have used
for
this.
problem solving.
Correct.
I think we had cases where we wanted to add two voltages in the time domain.
Yeah.
In one of the examples.
Yes.
Or currents. We have used it.
Yeah.
Same way, I think we had
We have taken e power minus as outside.
we have done all of that.
Yeah.
So we have had, I think, time domain function, the voltage which goes from some maybe 0 to 10 volts or whatever, and we wrote it as 10 u of t. In the Laplace domain, we wrote it as 10 by s.
Correct.
Right? Things like that we have done, or 1 by s
Correct.
and so on.
Correct.
So,
Correct. Then we have done, the differentiation, how it will become.
yes.
Just for formality, we'll write it down.
Yes. Because differentiation is a operation that comes up again, no?
Yes.
Time domain operation that happens.
Yeah. So, time integration. Just d by dt of f of t. This we did just previous class, no?
Just previous class.
So it was s f of s.
S times f of s minus f of 0 minus.
Yeah. In fact, if students want, they can also think about what is d square f of t by dt
Correct.
square.
Correct. That's right.
Then we will do time integration. Sorry, this here I wrote it as integration.
Oh, okay, okay.
Sorry. Yeah, so it was time differentiation. Integral f of t dt.
So I think 0 minus to t or something like that.
Yeah.
And I think this is
T is going and hitting the top
okay.
one.
Okay.
So it was f of s
F of s by
by
s.
s.
Correct. Correct. I think we did this in one of the previous classes.
Yes.
So
In fact, we have also taken a case where capacitor had some previous charge,
has a previous charge. Correct.
and that we got it as, suppose if the capacitor voltage was Vc of 0 plus is, let's say, 9 volt, then we represent it as 9 by S.
9 by S. Correct.
We have seen this, but yeah. Then maybe time shifting.
Time
We have
shifting.
just now seen.
Correct.
So that is f of t minus a,
Yes.
u of t,
U of t.
or u of t
Oh,
minus,
U of t minus a in
minus
this case. Correct.
That we got it as e
E
power
power minus as
as f of s.
Yes.
Okay. Then we have done something t f of t equal to
I think we did t times u of t, right?
t times u of t. We have done t times f of t also we have done.
T times f of t also we have done.
Correct.
Correct.
So if we have t times f of t, we had some nice expression. It was minus d by ds of
D by ds of
f of s.
f of s. Correct.
In fact, we use this to solve one thing in two ways.
In 2 ways. Correct. That's right.
Oh,
This is just multiplying a function by a ramp,
correct.
right? That's all it is.
Correct.
Yes.
So I think it's most of the operations are there.
Correct.
But then I was referring to some textbooks. There is something called initial value theorem, final value theorem, etc.
Okay.
Because that seems to be quite useful.
In circuits.
Yeah.
Actually, we have seen, no?
Ah,
When you're charging a capacitor through a resistor, we
Correct,
want to
correct,
find out
correct.
the final voltage.
correct.
I can see that.
So the corresponding one in S domain, what it
In
will
S domain, what it will be. Okay.
be. Okay. So
So initial value means you want to find out f of 0
yeah.
or f of 0 plus.
Initial value. So that means time t is equal to maybe 0.
0 plus or 0.
0 is okay, I think. So limit f of t.
Limit, I think we said, so t tending to
T
0.
tending to 0.
F of t. Correct.
That's in time domain.
That is in the time domain.
So in frequency domain, or sorry, in S domain,
In S domain,
it is limit S f of s.
And S goes to infinity?
S tending to infinity.
Yes. So, oh, I see. So, if you want to find out the initial value in the time domain, in the Laplace domain, you have to set S to infinity, multiply S times f of s and set S to infinity.
Yes.
Okay, I see.
It's not so obvious. Maybe we should try some example and understand.
We should try some example. Yes. What is an easy example we can try? Let's take a different function this time.
Sine wave or
Sine wave. Yeah, sine wave is a good idea.
There is one more theorem, then we will.
Then we will do that. Sure.
Like initial value theorem, there is a final value theorem. So in this case, it also says if time limit exists, there should be some time limit.
There should be some time limit.
Yeah.
Okay. So, okay, I understand. So there are some conditions.
Conditions.
Okay.
We will see those conditions when we solve problems maybe. So it's a final value. So that means
Limit t tending to infinity, no?
yes, limit f of t tending to infinity. which is again SF of S, S tending to
0.
0. This also has got some condition,
Okay.
but for now, let's assume that the condition is valid, and then we'll
Yes.
we'll see those later. I think these are the most, we have covered most of the operations
Yes.
and the corresponding S domain operations.
Yes. Okay.
So this will be helpful, I think, when we solve,
Absolutely.
when we operate in S domain.
Yes.
So you were saying initial value we will try in
we should try on something, no? Maybe even
So-
final value for some RC charging we can try because
Okay.
we know the final value. We'll take some simple example for
Okay.
both.
So first we will try this initial value theorem.
Yes.
I'll take a fresh page. I have this theorem. Okay. What do you want to do? Sine wave, huh?
Sine wave.
With some angle.
Shall we do some angle? Sine wave means it will start from 0.
0.
We already know.
Correct.
Sine wave when it starts, so we'll do sine omega t plus phi.
So I have
F of t is a sine omega t plus phi.
1 sine omega t.
So now if you want to use initial value theorem,
Or I have to convert
you
it
have
into,
to find out capital F of S. But we
Yes.
already did this.
yeah. So f of s, I think it was,
We'll go back to the table
yeah.
to confirm.
Here it is.
Here it is. So it is omega cos phi
Yeah.
plus S sin phi. Okay.
So we just have to apply this.
So S times F of S and take the limit.
So not time. S tending to. Correct? Huh?
Yes, correct.
So this is S omega
Cos phi plus S squared sin phi.
we will separate it and write.
Yes,
That may be easier.
that may be easier.
So we'll bring this S to denominator.
Yes.
So this will go to 0.
0 as S tends to infinity.
Then we'll have omega cos phi by infinity. That will also be
0.
0.
So this portion seems to go to 0. But
this-
let's maybe draw the next part.
Yeah.
We'll add the next part and see. So
S
it will be
square sine omega
Sin
sine phi.
by S squared plus
So I'll
omega
bring this
squared.
sine square. So
Correct.
that is 1 plus
Omega squared by S squared. Correct. Okay. And now omega squared by S squared goes to 0.
This goes to 0.
Yes.
So it's sine phi.
It is just sin phi. So this is 0 and this is sin phi. Let's look at the time domain function. You said t equal to 0. Oh, it is sin phi.
Because t is 0.
T is 0. So in fact, in this case, it's a simple example to prove it.
From here we know,
Correct.
but we have proved
We have shown that the initial value theorem gives the same answer.
it works.
It works. If it was a much more complicated function,
It would have.
it would have been. There
More
are cases
useful.
where it is more
Yeah.
easier to do it in the Laplace domain.
Nice.
Correct.
So should we try?
Shall we try one simple RC charging?
Hmm.
Because we know the answer. We have already looked at that circuit before,
Hmm.
some circuits before. So we'll try some simple RC.
What shall we do?
Let's take the values of the resistor as 1 ohm, capacitor as 1 ohm, and let's say input is u of t,
Yeah.
or 10 u of t, for example.
One ohm and
Let's say 1 farad.
1 farad. Really large capacitor.
Really large capacitor, yes.
Okay. What am I supposed to do?
So we want to find out the let's say final voltage across the
Across the
capacitor.
capacitor. V of t or Vc of t
Vc of t. We want to find out Vc of infinity
at
at
t equal to infinity.
correct.
So that means I should have an expression for Vc of t.
Correct. Well, because we don't know what it is, let's do it in the Laplace domain directly. Right? Because now we have to write the differential equation
Yeah.
and solve it.
So we'll completely
We'll
convert
completely do it in the Laplace domain.
Otherwise, why we learned all this, correct?
Yes.
So this is 10
10
by,
by
s.
s.
This is just 1 and this is
1 by SC. In this case, it is just 1 by
1
S.
by s.
Yes. Because the capacitance value is 1.
Correct. So the voltage is
This is just a voltage divider, no?
correct. So Vc of s
Yes, Vc of S.
is equal to 10 by s divided by
1 plus 1 by S
plus 1 by s into,
into
1
1
by
by S.
that is 10 by s by s plus 1 by s. S will cancel into 1 by s. So 10 by s into
S plus 1. Correct. And now we can apply.
okay. So we'll do everything here only.
We'll
S
do
domain
everything
only.
here. Correct. So S times Vc of S.
I'll write at the bottom. Let s f of s tending to 0 is 10 by s into s plus 1.
And then you need S times that. This is easy.
S and s will get
S and
cancelled.
S will get cancelled. And this is just 10.
Oh, s tends to 0.
S tends to 0. 10 volts. So Vc of small Vc of infinity is 10 volts.
Because anyway the capacitor will finally charge to
Correct.
10 volt.
That's right.
Again it is working.
Again, it is working. So this is a theorem that will be used in specific situations
Yeah.
to calculate, both these theorems, initial value, final value, will be useful.
So what you're saying is they are not just for the purpose of having there. I mean, they have some use.
They have
actual
some use. Correct. So the one thing to remember is that if you look at it purely mathematically, there are some limitations.
Yeah.
But they will learn about it later.
Yeah.
I think in a future, at a later time, they will learn what the limitations are.
Yeah.